Okay. Perfect. Okay. There we go. We're live. Hi, everyone. Thank you for joining our Elastic user group for Chicago. My name is Olivia, and I am a community program specialist here at Elastic. I'm joined today by Praveen and Shri from Egen, also located in Chicago, and they will be presenting on a day in the life of an Elasticsearch architect. We'll have time for Q&A at the end, so please feel free to add your questions to the chat, and we'll get them answered at the end. And with that, I'll turn it over to Praveen and Shri.
Cool. Thanks, Olivia, and welcome everyone. I'm Praveen Salitra. I have Shri with me. He's an Elasticsearch certified engineer, working as senior software engineer here at Egen. So today we are going to be talking about some of the decisions that you have to make and some of the concepts that you have to be aware of, especially when you are dealing with Elasticsearch and managing it and those kind of things. So we will start with that sort of discussion, but a couple of minutes talking about our company Egen. So we are, of course, as Olivia said, we are located here in the Chicagoland, in Naperville to be specific, and we are a company of cloud and data engineering experts. We have been working with some of the unicorns from Chicago and then a lot of enterprises around the US as well. We have partnerships with AWS, Azure, and Google Cloud, so all the three top cloud providers, but then, of course, Elastic as well as Confluent as well in the data side. For the last 6 years or so, we have been working with several clients and customers, and then, of course, projects involving industrial IoT, retail, healthcare, fintech, and then, of course, these days we have started working with few HR, payroll, benefits kind of customers as well. So that's about Egen. Let's get started for today. So the agenda for today, actually, when we looked into the timing and all that, we thought probably one session is not going to be sufficient to talk about architecture as well as administration or operational things with Elasticsearch. So we have broken it down into two different sessions. Today, we are going to be focusing on architectural decisions. And of course, there we will be looking into overview of the Elasticsearch architecture, some of the concepts that you should be aware of, that everyone should be aware of if you are planning to use Elasticsearch, how to organize data in Elasticsearch in terms of indices and shards, and then what is a resilient Elasticsearch cluster, what are the concepts behind it, and then, of course, how do you size an Elasticsearch cluster if you are starting from scratch, right? So that's what we're going to be covering today with a demo, full-fledged demo that she will be doing. And then on November 3, on Wednesday, we will be talking more about operational challenges and things that you will be doing once you have Elasticsearch cluster up and running. So we'll be talking about how do you provision Elasticsearch cluster these days, especially if you want to use ECK or Elastic Cloud for that matter. Scaling Elasticsearch cluster, of course, ILM, and then monitoring piece of it, and then, of course, snapshotting and restore as well. So for today, we are going to be focusing mostly on the concepts and then a demo related to that. So let's get started. So first, let's dive into some of the fundamentals, right? Now, everyone probably is aware already here, Elasticsearch, or the tooling that we are going to be talking about today, the search feature is actually based on an open source Java engine called Apache Lucene, right? And that is the backbone where search is getting executed, right, behind the scene. So it uses the concepts of inverted index and edit distance for implementing or for providing you a fuzzy search, right? I mean, you may have seen or creating Elasticsearch underneath behind the scene at the very low level. This is Apache Lucene is going to do the job for you. So what's the problem? Why can't we just use Apache Lucene forever? And then why do we need a layer on top of it? So the problem or the challenges are when you want to scale Apache Lucene horizontally because of the overhead. What if you want to have multiple Lucene instances? How do you orchestrate them? How do you manage them? And that's the job loosely that Elasticsearch is trying to do on top of it, right? So think of Apache Lucene as the underlying engine and then Elasticsearch as an overlying service on top of it, and doing not just search, but then a lot of other operational things as well on top of this layer. So the first concept that I think we should be talking about today is a shard. So think of shard in the Elasticsearch concept as an individual Lucene instance running on its own, of course. So that's the shard that you have. And then what it does, of course, the real data that you are having is going to be stored within the shard, and it will be either a primary shard or a replica shard. Why that? Well, because in order to achieve the high redundancy of the data, that's where Elasticsearch will allow you to specify how many replicas you need for a primary shard. So data that you are indexing into Elasticsearch, that is written to the primary shard first, and then replicated to one or more replica shards. That is just definitely to increase the redundancy, increase the replication. If something goes down with primary shard, or the node goes down where the primary shard is hosted, then at least Elasticsearch knows that, okay, I can still look into the data which is on the replica shard for that particular primary. So all this promotion of replica to primary, that will be taken care by Elasticsearch for you. So that's one of the pretty good things with respect to Elasticsearch. Moving on, now let's talk about the concept of index, right? So very simply put, it's a collection of JSON document. But behind the scene, of course, it's a logical grouping of all the shards that you can have for a specific index, right? Including primaries and replicas. For example, here on the diagram, think of it like you want to store all the orders placed in an e-commerce platform, right? If you want to store them in the single shard, that's possible, but then there are some practical limitations. We'll talk about them a little later. But let's assume that you have distributed all that order into 3 shards, and you are telling in Elastic that, hey, whenever I want to store the index the new orders, you figure out which shard out of primary 0, 1, and 2 you want to store, if it's the default routing, and then Elastic will do the job. Behind the scene, we can tell Elastic that, hey, for each primary, make sure you have 1 replica, at least minimum 1 here. You can have more than 1 as well. So that's, of course, the index that you have. Now, what if you have limitations there where you want to have more than 1 index? So, for example, let's say you have orders and you are growing, or your e-commerce platform is receiving so many orders that 1 index is out of picture from the practical bounds of the storage and all that. So you may think of a scenario where you have orders or indices created by months, right? So you have an order index for January, February, and so on and so forth until the last month or so, right? Let's say September. But your applications, they do not probably want to deal with individual indices, right? Or individual index naming and all that. What if you want to do some operations? You maybe want to merge few indices, or maybe you want to do reindex and things like that. So if that is the case, what you deal with, what you deal your applications with actually is some concept called aliasing. Think of an alias as a secondary name for a group of indices. So you can create an alias, for example, here, orders, and then you can refer that into the application. Application doesn't know how many indices are there underneath. And for example, you may have 2 more, one for October and one for November this year. But your application doesn't have to be aware of that while querying, while searching for orders. And that's the benefit with aliases. You can do 0 downtime, reindexing, rolling over, and many other things with respect to operational dealing with indices as well. So that's the beauty with aliases. Now, from there, of course, all these things that we discussed would need some sort of compute. That means CPU, memory, and then, of course, disk as well. And that's where a node comes in picture, right? A node, think of it like either a virtual machine or a Kubernetes pod, or anything that can provide CPU, memory, and disk to your Elasticsearch service. So for example, here we have that, and then of course Elasticsearch service instance is running there. Now a node can assume multiple roles. In Elasticsearch cluster, a node can have, last time I checked, I think around 12 or 12 plus roles, and then it can have any combination of those. So for example, here, a node, for example, can have a master and a data and an ingest node, ingest role all together on a single node. So that's possible. If you don't specify this on the node configuration, then the node assumes all the roles possible there within the Elasticsearch version. So for example, here, I have specified role of master and data on the single node, and that is possible. And this is Elasticsearch node, okay? Just to be specific. And then of course here, since it's the data node as well, it has the data, meaning some primaries, some replicas of some indices, apart from, of course, the Elasticsearch and the tooling with that. So that is node. Now, on top of it, so you see the pattern, right? We started from the ground level, and then we are going 1 layer up and up. And now, of course, we are talking about cluster. So a collection of connected nodes, or a collection of Elasticsearch nodes, is actually a cluster. And you can have minimum 1 to a practical limit there. You can have as many as number of nodes there. In this example, for that matter, we have a cluster of 3 nodes. All of these 3 nodes have shared rules. So each node is a master as well as a data node. And of course, an Elasticsearch instance is running there, or a service or a process is running. Since it's a data node, it has data shards as well. Among the nodes, they are communicating over TCP. And then from outside, if you want to make requests, you, of course, are going to be using HTTP API or RESTful API, which is very, very powerful feature in Elasticsearch. So the good thing about Elasticsearch cluster and the nodes within this cluster is each node knows the whereabouts of where is the other node. And then they are aware of if something goes down, then how to handle that scenario. Now, as I said before, each node can accept a client request. And that means you can that means Elasticsearch inherently has this load balancing concept. You can put an external load balancer as well in front of Elasticsearch cluster, but then internally as well. Let's say if you want to send a request for search or indexing, you can send it to any node and it will figure out how to deal with other nodes on its own. So that's pretty solid. Now, with all these things within the cluster, there are few settings, there are few configurations that we call cluster state. So what are these? Of course, what are these nodes? What is the configuration of the nodes? Where are these available? IPs and a lot of that metadata as well. Other settings of the cluster in terms of how many nodes you have, what's the name of the cluster, what's the current health of it, and then some stats and things like that. How many indices your cluster is having, where are those mappings, or what are those mappings, and where some settings related to those indices as well. And then, of course, an index is broken into shards, right? Primary shards, and then they may have replica shards as well. Where are the shards of a particular index? That is also part of something called cluster state. Why it is important? Because this is one of the things that will put some sort of practical limit on the sizing of the cluster. So theoretically, you can, of course, have minimum 1 number of nodes in a cluster, and there is no limit on how many nodes you can have within a cluster. But there is actually a practical limit. I'm not saying it's 100 nodes. I'm just saying if you grow a number of nodes, this is the size that we have played in the Elasticsearch cluster as far as number of nodes are concerned. But there are a lot of operational challenges. Of course, with larger nodes cluster, you will be able to fit in more data, right? Meaning you will be able to search more data, and that's inherent, of course. But then it will create a larger cluster state that will be harder for master to manage, right? At a time, there is a one master node, elected master node, and that particular poor guy is going to be handling entire cluster state. And if you have the larger number of nodes or more nodes in a cluster, that state is going to be larger, and it will be some unnecessary CPU spikes you will see, or the patterns you will see. Even if you are not doing any indexing or search in that large cluster, you will still see your CPU usage is very, very high, and you will be like, what's going on? So you will be dealing with a lot of operational issues if you have large cluster. In our experience, we have seen around 100 nodes, but then you can find that sweet spot depending on how is your indexing pattern, how is your search pattern, and other things regarding that as well. Now, good thing is in the newer version of Elasticsearch, also on Elastic Cloud now, cross-cluster replication and cross-cluster search is now available. So you don't have to keep on creating a monstrous cluster, right? You can, again, scale from the cluster perspective while putting more than one cluster for your use case, and then use the options of cross-cluster search. So these are some of the concepts growing from Apache Lucene shards to a very high level of cross-cluster search, very, very brief. So let's see how a typical large production cluster will look like. So in this scenario, we have 3 master nodes, right? And these are 3 dedicated master nodes that you should have in a typical very highly available production cluster. So assumption here is, okay, we have 5 data nodes that are going to store the data. There will be no data stored on the master. So assume you have an index, the red index, index A, and it has 5 primary shards. So, and then each primary shard can have 1 replica. Let's say that's how we have configured. So what we can do, or when we start indexing, or when we create this index, Elasticsearch will try to make sure the primary and its replica are not on the same data node. That is just to avoid issues. If data node goes down, at least it should be able to find a replica for that primary shard on that data node somewhere else. So that's the whole idea. So in this example, if primary shard 0 is on data node 0, then Elastic will definitely try to put the replica of that primary shard onto data node 2, and same story will repeat for others as well, right? So pretty simple example, or one such option that Elasticsearch will go for. Let's say if you have another index B and then you have 3 primary shards there, then in that scenario, that's how it will, when you create that index, Elastic will again try to do the same. It will put the primary shard of the 0 on 1, data node 1, but then it will put replica somewhere else. So that's the whole idea there as well. I will quickly go from there, but you get the idea, right? Now let's talk about masters. They have a specific role and a lot of responsibilities within Elasticsearch cluster. So here, for example, assume you have 3 master nodes. They are talking to each other. The most important piece, well, one of the important pieces, there will be only one master at a time, which is going to be called elected master, right? And then what these master nodes will be doing. So they are in charge of lightweight cluster-wide actions. For example, making sure any update on cluster settings, they will be taking care of it. If you are creating or deleting indices and the settings, master nodes will be involved. If you are adding or removing any nodes to your cluster, master nodes are going to be involved as well. And then deciding on shard allocation of the nodes as well. So that's going to be the responsibility of the master nodes. Now that if assume the assumption is, let's say if master 1 is the elected master right now, so in any cluster you need to have a stable master node. If you don't have it, your cluster health will be red in that scenario, and your cluster may not be usable. So it's very important to have an elected stable master node for the cluster to survive. Now in Elasticsearch, you can add nodes, and then they can assume multiple roles as well simultaneously at the same time. So our suggestion is for the small clusters, you probably may not want to have dedicated masters and dedicated data nodes. Most of the use cases will be okay if you share these roles, and you can go ahead with the shared role of master and data on the same Elasticsearch node, and that's going to be perfectly fine for a smaller cluster. Now, if you have a very large cluster or some sort of dedicated things you want to put in, you can have and you should have dedicated masters and dedicated data nodes. The diagram that we showed on the previous slide, just like that. So you have 3 dedicated masters there, and then 5 or more dedicated data nodes as well. And that you can do easily by configuring a property called node.roles, and then you can assign what role you want to have this particular node, either master or data. So that's the whole idea. Another beauty with respect to having dedicated master nodes is that your masters are not doing search operations. Your masters are not doing indexing or store operations, right? So your dedicated masters, if you have, they don't have to have same compute resources as the data nodes, because your data nodes will probably require 1 or 2 tier higher in terms of the CPU and memory configuration. And if you have dedicated masters, you don't need to worry about that actually. So that is about the master nodes. Now, what if, let's say if you have the cluster up and running and your master goes down, right? So let's jump into what is the process in which Elasticsearch will elect a new master. So let's talk about that. So as I said before, right, there is a single elected master node within the cluster at a time. And if that selection actually is done when the cluster starts for the first time, and then if the current master goes down, then a new master will be elected. So that's the whole idea. Now, how does Elasticsearch does that? So it uses a quorum-based decision-making for electing that master node. And that is to avoid a scenario where what you call the split brain scenario, right? Let's say if you have 3 nodes, and if one of the master goes down, these 2 should be able to figure out and elect master between these 2, right? Master 0 or 2. Assumption is, let's say in this case, let's say master 2 is the next master or next elected master. So that's why, because of this quorum-based decision making, you need to have responses from one more than half of the master eligible nodes within the cluster. So if you have the master election process going on, you want to make sure you always have one more than half of the master eligible nodes when this process is going on. Otherwise, your cluster will be in a deadlock or will be inconsistent. It will not be available. Now, you can always add or remove master eligible nodes to a running cluster. The best thing now with Elastic, I think 6 or higher, or maybe 7. How many number of master eligible nodes it should have, and what is that minimum thingy? Elasticsearch will maintain that automatically for you, or what we technically call the voting configuration. So that's now the responsibility of the Elasticsearch service as well. In the previous version, you had to configure a property in the configuration that, okay, how many minimum number of masters you would want to be selected in the election process. One other thing on that looking at this one more than half of the master eligible nodes requirement, if you want to stop master nodes, make sure you do not go and kill more than half of the master eligible nodes at the same time, because then this will not be hold true, and then your cluster will go into the red state or will not be even available actually. So keep that in mind. That means if you want to ever stop a node, or maybe you want to do any sort of maintenance work or upgrades or anything, you can probably do it better if you follow rolling restarts. Take one master node down, let Elasticsearch cluster stabilize, upgrade it, and then attach it back and take the another one down at that point. So that's one of the other important things. Cool. So we understood the differentiation between dedicated master nodes and shared roles. We talked about the minimum number of, well, we didn't talk, but we talked about the master election process now. So let's see what is a resilient Elasticsearch cluster. A cluster that can handle if a node goes down, if a data node goes down, if a master node goes down, or if you have a multi-AZ or multi-availability zone cluster. Even if an AZ goes down, your cluster should still survive. So what is that? How do you do that? So in order to achieve that, you want to make sure your cluster is redundant for every required component. What does that mean? Well, it means the cluster must have at least 3 master eligible nodes. Now, depending whether it's large or small cluster, you can have dedicated masters, shared masters, doesn't matter, but at least 3 master eligible nodes have to be there. At least 2 nodes of each role. So let's say if you have data nodes, don't ever go with one data node only in a cluster, because if that goes down, you lose all the data unless you have snapshots and backups and other pieces. And then for each shard, each primary shard, I should say, you have at least one replica. Okay, you can have one and more replicas, but definitely have one, so that Elasticsearch can recover if the primary shard goes down. So for the small clusters, as I said, you can probably start with the shared rules with data and master on the single node. Definitely you want to have minimum 2 master eligible nodes, and if you are running on cost issues and you want to save money, just have one more voting only master eligible, which is a tiebreaker node. It's a specific set of rule for this particular node. It's not going to do anything. It's just going to wait for the master election process and then take part in it. If you want to do that, I would say avoid that. I mean, instead just go with 3 shared nodes which have data and master node shared on each of the node, right? So why do that minimum cost cutting or shortcut there? Just have 3 shared nodes which will have all 3 as master, and all 3 will act as data node as well. And again, we are talking about small clusters. For the large cluster, definitely have 3 dedicated master eligible nodes, as I discussed before. And if I'm worried about availability within AZs as well, within your cloud provider, then of course have zonal redundancy with 1 master eligible node out of 3. So 1 in each of the 3 zones, right? So you should think of at least 3 zones within this region, within this cluster, and each master sitting in one of the zones. So even if one zone goes down, that means one master goes down, you still have 2 master eligible nodes to elect themselves a new node or new master for the cluster, right? And then of course, you can still think about cross-cluster replication, so that even if the entire region goes down, you have other region cluster available out there. So depending on your SLAs, you can think of how you want to start and then how large you want to grow. You can go into multi-regional cross-cluster replication as well. Of course, it's very tedious, and that's where Elastic Cloud comes into picture. But the rest of them you can do, you may try to do it on your own as well using ECK or anything else. So let's now talk about how do you size Elasticsearch cluster, because that's going to be the first thing you will be asked. Maybe your product team wants your teams to implement search on the objects that they are storing in some sort of relational data store, right? And they are coming to you and saying, hey, we have a lot of documents, we have a lot of files, we have a lot of these objects that we are storing in the relational data stores. We want to enable a search like what Slack does, right? So they will be coming to you, and you will be thinking about, what are the points I should be aware of? And the first is sharding strategy, meaning how do you create shards? How many do you need? What are some of the important points that you need to consider while creating shards? So by default, an Elasticsearch index has 1 primary shard by default. And I think this setting has changed in the version 5 or 6. Previously, you used to by default have 5 primary shards for each index. But then in order to avoid the confusion, they have now straight away went and configured to have one primary shard by default for each new index that you create. And of course, if you want to alter that, definitely you can set that to a higher value when you create the index. The important thing is you can increase it to a soft limit of 1024 by changing this property when you create the index. But then if the index is already created, let's say with 5 primary shards, and then now during the life of that index, you want to increase number of shards, you can't do that on an existing already created index. You have to recreate a new index, move over the data, which is what is called reindexing, right? So if you ever want to play with the shards, the best time is actually at the creation of the index. Otherwise, you will be dealing with reindexing. So just to identify, okay, how many shards are we talking about? Because there is a specific factor, practical limit that you will see in the next few slides. So you have to understand how to count total number of shards, right? So let's say if you have an ordered index and you have for some reason configured 4 primary shards, and each primary is going to have 2 replicas, then of course you are talking about a total of what, 12 shards here, right? So primary will be replicated twice now, just to have 2 levels of redundancy. So even if a primary goes down, one more replica goes down, still you have all the data sitting in other replica, and Elastic will try to make sure that all these 3 are on 3 different nodes within the Elasticsearch cluster. So you have to think about how many number of nodes that you should have, and how many shards that you should create, and how much should be the replication factor and things like that. So now, what is the benefit of more primary shards, right? Because with more primary shards, you are getting more parallelism. In what sense? So let's say you are sending an index request to Elastic and say, hey, I have this 1,000 objects I want to store in the Elasticsearch. If you have more primary shards, meaning Elasticsearch can now distribute all that 1,000 objects into multiple primary shards there, let's say 5, if you have that configured. And instead of throwing it to 1 shard, now, of course, you are throwing it to 5 shards. So a little better performance, of course, from the indexing perspective. But and again, the keyword here is a bit slower. You may encounter a bit slower search performance. It may be there, it may not be there. It all depends on what size of data you have, how you have done the mapping. But still, theoretically, you may have a slower search performance as well there, because now your coordinating node, the node that is getting the request, needs to talk to multiple nodes probably to get understanding of all the shards and where that data is when the search phase is going up. So there are a few important things, especially when you're thinking about shards and how many you should have and what are the limits there. The first and foremost is aim for the shard size anywhere between 10 gigs to 50 gigs, right? Very huge range you will find here, but that's what it is. I think in our experience, do not go more than 50 gigs in terms of a single primary shard size, okay? For search use cases, I think stay to middle, which is 25 gigs or so for each of the primary shard. What's the problem with larger shards? So what happens, let's say when a node goes down, a data node goes down, Elasticsearch actually may try to move the nodes or to, well, not when it goes down, but let's say when you are trying to run the maintenance on an Elasticsearch node, Elasticsearch may try to move those shards to other nodes, right? If you have larger shards, then it will take more time, and then it may be inconsistent as well. And if something goes wrong, it may be harder for recovering from the failure as well. So the best idea is to keep somewhere between 10 gigs and 50 gigs, and then for the search, hover around somewhere like 25 gigs or so. The other thing is relation of number of shards with respect to how much heap memory that you have. Again, Elasticsearch is based in Java, so the concept of heap is important, or JVM heap. So aim for somewhere around 20 shards or fewer per GB of heap memory. So if you have, for example, a node with 30 GB of heap memory, then you are looking at the max of 600 shards. And that is the limit where you cannot go crazy with number of indices as well within Elasticsearch, the problem which is called oversharding. So that is and 2 important concepts that we have discussed, right? Now let's talk about how many shards you can have, right? Assuming you already know how much data you have that you want to put it within the Elasticsearch cluster. And then the question is how many nodes you want to have, right? And what should be the configurations of those nodes? How much CPU you should give, how much memory you should give, how much disk you should give to each of the node within that cluster. So we have come up with some simple formulae. These are based on our experience, but then also a lot of reading from other companies as well, including some cloud providers. So the simple formula that has worked out very well for us is in terms of number of shards. If you want to calculate how many shards you will eventually have, assuming you have how much data you want to store in the Elasticsearch cluster right now, plus in the future as well, which is room to grow, multiply that by 1 plus have some additional indexing overhead criteria as well, and then just divide by what is the size of the shard you would want. So pretty simple formula. The source data plus any room to grow, and then 110 or 1.10 multiply by that, and then of course the total divided by the optimal shard size you would want, anywhere between 10 to 50 gigs, right? Now, how much disk space you would need total? So if you have source data already figured out, then you can just multiply 1 plus number of replicas. So if you have 1 replica, this entire thing becomes 2. If you want to have 2 replication for each primary shard, then this becomes 3 times the source data, right? And then you multiply by a factor of 1.45, 45 indexing overhead, Elasticsearch overhead, Linux kernel overhead, and things like that. So this is one of the things. And then comes, okay, how much CPU and memory you should be giving to a node. Now, in our understanding and our experience, for a cluster handling complex aggregations, search queries, high throughput of, and then frequent updates, I think what has worked out well to start with is actually start with a node config of 2 virtual CPU cores and 8 gigs of RAM or memory for every 100 gigs of storage that you have calculated here. So that's a simple formula that you have at least 3 of them. And then another point with respect to JVM is you cannot have, or you must not have more than 50% of the physical memory assigned to the heap. Okay, so that's another piece. And then maximum you can only have 32 gig of heap size in a Java environment. So that is another thing you have to keep in mind. So let's assume, let's do a very simple calculation. You have 150 gigs of existing data that needs to be indexed, right? So how many shards you will have, especially the primary? Well, if you don't think of any growth, maybe this is all the data that you will ever have. And then you can just put that into the formula, and then you come up to let's say we want to have each shard with 25 gigs max. Then you are looking at around 7 shards that you can start when you think of creating a new index. But if you think in a year you will grow 100%, you already have 150, you will grow 150 gigs more, apply the same formula, your desired shard size is 25 gig, maybe you want to apply or implement search, then you are looking at around 13 shards. Why these things are important? Well, because you cannot change the number of primary shards once the index has been created, unless you want to do re-indexing or you want to do index rollover. That's a separate concept. We'll take care of it. We'll talk about this in the next meetup. But those are some of the things you have to think about. Now, what about, let's say, we understood in the previous few slides about minimum number of nodes has to be 3, right? Let's assume we start small. It's a small cluster. We'll have shared roles, and then we'll have 1 replica per shard. So how much disk space in total are you thinking of? So with 150 gigs of data that you have, if you put it into this formula with 1 replica, you are looking at somewhere close to 435 gigs of total disk space, right? And then in terms of compute and memory, I mean, we talked about having, if you have 100 gigs of storage, assign 2 cores and 8 gigs of RAM, we have 435, you do the simple math. And then of course you're looking at some weird number of 9 CPU cores and 35 gigs of RAM or memory for your Elasticsearch nodes. And then if you think about having 3 nodes, you can do one more division. And then of course you are looking at somewhere like 3 nodes, each having 3 vCPU cores, 12 GB of RAM, and then of course 150 gigs of disk storage per node. And the cluster will have 3 nodes. In total, it will have all of this 2-3 metrics that you have there. Now, with 12 gig of RAM that you have here, right, you can set JVM heap size to 6 gigs, right, the 50%. And technically, you will be able to accommodate 120 shards with the formula that we discussed on the previous slide, where we talked about 20 shards per GB of heap. It will give you 120 shards per node, and in total within the cluster you have 360 shards in total, right? These are all the ideal factors. Now, depending on the use case, this formula may not be true, although we have tried to use this formula for many of the use cases, but every use case may be different. Maybe you are dealing with files where each single object is 2 gigs. These things may not work out, right? If that is the case, I would suggest benchmark your setup using a very awesome tool called Rally, again from Elastic. And there it will help you to set up and tear down Elasticsearch cluster. If you want to do any benchmarking, any management of benchmark data and specification, even across ES versions, You can run this benchmark and record their results, and then of course find the performance issues, and then you can of course handle with the telemetry devices as well. So pretty good. Even you can compare the results as well. So that's a very important tool. Probably we'll have and talk about this in some other meetup down the line. But this is a pretty good tool that we recommend to do the benchmarking at the start of your first POC, or when you are trying to go with Elasticsearch for the first time. So the last piece to discuss before we go into the demo is multi-tenancy, right? How do you organize data if you have multiple clients? I mean, the easiest one, but the most costly is, of course, having each one cluster per tenant, right? It's going to give you best isolation of network, compute, and storage. Of course, if you have more, you need a very high degree of automation in order to create and manage and maintain and operate these clusters, because these are all independent clusters now. And then, of course, monitoring and operations are going to be difficult as well, right? You can also have an index per tenant within the same cluster. Logical isolation, of course, with access control you can achieve. But you will quickly run into a problem called oversharding, where you will have too many smaller shards. And then if you remember the count or the formula that we had on the previous slide, where practically you are limited with how many shards you should have within a cluster. If you have one index per tenant, you will run into this issue with the larger cluster state as well. And we don't recommend going with this approach. The best approach in some scenario is to go with one document per tenant. It will make your scaling super easy and best suited for search use cases for sure. You need to have a tenant ID now, a field on per each document, each object that you're going to be indexing within the Elasticsearch. And then for all the operations that you do, whether you do the search or the indexing operations or requests, you have to now scope those requests with a tenant ID. Otherwise, you will leak the information, you will leak the security concern as well there. And then, of course, you have to have very strong access control mechanism within your apps when they are communicating with Elasticsearch, because again, all the documents or all the tenants are right there, right? So you have to make sure the scoping logic works flawlessly. And that's the recommendation from us. I mean, if you are just having 2-3 tenants and these are very large tenants, maybe they are paying you too much as well, then definitely go ahead with work cluster per tenant approach if that works out. Otherwise, if you have self-serving onboarding for the new clients, new tenants, meaning you will not be there to create their own clusters when they join you, like Slack, better to use if you have better to use document per tenant approach there. Cool. So let's jump into the demo. We have a few minutes remaining. I'm just going to walk you through the cluster setup that we have done for this particular demo. What we did was we are creating this Elasticsearch cluster on Azure's Kubernetes service. And that's how we typically do this time. For this particular demo, we have 3 AKS nodes, each having 2 cores and 8 gigs of RAM. On top of it, we are running Nginx controller for handling the service communication from outside world to the internal services. And then, of course, we have a cert manager to handle the certifications, SSLs, and all that. Again, these things have nothing to do with Elasticsearch so far. The first thing you would install after this is something called Elastic Cloud on Kubernetes, the ECK operator, right? It's I think basic license at this point, which is available for free, and then you can run it on any Kubernetes distribution. In this case, we have Azure Kubernetes Service, but you can run it on EKS, GKE, or your own created Kubernetes cluster using something like KOps. Once you have that, I think I will just talk about the same cluster, 3 master nodes. One of them will be elected, 5 data nodes. And then on top of it, we have using ECK, you can also run Kibana. And then this is the Kubernetes service that the ECK has created for communicating and doing this load balancing within the cluster. From outside, we're going to be reaching out to Kibana using the Ingress controller or the Nginx controller. And then we can also reach out to the Elasticsearch as well. So I'm just going to hand it over to Shri, and he can take care of the demo going forward on this setup that we have done. So over to you, Shri.
All right. So can you hear me?
Yep.
Okay. Awesome.
Not the screen, but we can see you. Yep. I think the screen is starting now. Perfect.
Can you see the screen now? The main Kibana.
Yes.
Awesome. Okay. So hi guys. My name is Sriharsha Datla, currently senior software engineer at Egen, as Praveen introduced, and let's just right into the demo actually. So currently, as we just explained about the cluster setup, so we are actually in a secured cluster, which we set up on Kubernetes on AKS. So even though, so that's why I wanted to log in here in front of you so I can So I have my user on me, and then that's it. So that's how clean it is. And this is actually the Kibana. We probably would go one more time about much more other things that Kibana provides, which are pretty cool operations and cool tools. But let's get into demo part first, and then just before giving you one kind of overview. So high level overview is like different commands here, and currently to show that, so this is my cluster health. So this is a cluster name, and then currently it's green. And for you to get the list of nodes, you can just do what are the list of nodes that I have. So here you can see what are the list of nodes that I have, different data nodes and master nodes. One thing to note whenever you do this command, or you execute this command is here you can see that, what is the node role that this particular node is actually responsible for. And this is currently three masters, but the one that you see with star or asterisk is actually the elected master. Okay, so currently in this case, master 0 is the elected master, right? So I also have a couple of terminal windows open. So just to give an overview, so when I do kubectl get pods, this is one of the command that I can run to get the what are the pods that Kubernetes are set up, and then we can see that each pod is actually a node, and you can see 0, 1, and 2, and this terminal is actually for master node log. So 0, 1, and 2. Similarly for data nodes, all the data, all the 5, 0, 1, 2, 3, 4, 5. And so yeah, so that's basically the setup. I'll come to the app, which is actually writing to the Elasticsearch right now, but let's see. So we get to the nodes first. That's good. We got to understand what are the nodes, and then we go to the shards. So here are the shards that we have. So list of shards that are actually set up on these nodes, right? All the dots that you're seeing, what are the indices? These are actually by default what are the inbuilt indices that Elasticsearch uses for Kibana, for all the other internal mechanism, right? So if I want to see my indices, I can actually do this. Same thing. So they'll have like multiple indices. And before start of the session, I actually created one index called orders 2021 October. And then this is actually almost the usual, syntax that we would use. You would set up what is the alias. Briefly, we explained about what are the alias earlier. We'll go much deeper into the next session. But then we can go to the settings, and here is very important point. I actually gave the number of shards stand for number of primary shards, and then number of replicas stand for what are the replication factor to it. So there are 5 primary shards, and there is 1 replica of each, right? So just remember this two, 5 and 1, right? And there are few other settings that we actually turned on, and especially we gave the log level as trace, and this is particularly for the log for the demo purpose. So we'll get back to it very short time. And then of course I created mapping to it. Mapping, if you're just very new to Elasticsearch, if you're coming from relational, it's just kind of, you can imagine like a schema for the columns or for the fields that you're going to shape in Elasticsearch index, right? So just like high level schema, we'll go much more details into why you actually need to give a mapping, what is a dynamic mapping, sorry, dynamic mapping, and then static mapping, and all those things later in next session. So yeah, so we have an index here, and I also can get the list of indices here as I just showed earlier, and we have orders index here listed down. Five primaries, 1 replica, currently 2,000 documents, 2,001 documents, and then the size of it, right? Now we have to check what are the actual shards that this index is on, and that we can check like this with this call by giving the index name. And here you can see, as I was saying, like 5 primaries and 1 replica each. So there will be total of 10 shards, right? So here I actually can the shard, and you can see that, okay, the 0th shard, the shards with 0 actually, primary of it is actually getting data 3, data node 3, and then the replication of it is data node 2. One thumb rule of Elasticsearch is there can never be a scenario where a primary and replica would actually stay or would be stored on a single data node. That can never happen. Elasticsearch would not even allow that. So that's just a thumb rule to remember. Now, who is writing the data to this particular index? So I actually have a small, simple, very basic Python app. I actually have a big set of JSON, which is actually having user data. And then, so every 2 seconds, just connects to uses Elasticsearch Python client and then just connects to it and just writes the data to it. That's it. So very basic stuff. This is just to give you an idea of how the data would be stored to Elasticsearch, right? Now this is all simple, right? Now let's go to one thing, right? Now let's do the demo part. So here we saw the nodes, and of course we saw that Elasticsearch meetup master is actually the elected master, right? Now let's see how resilient Elasticsearch cluster is, especially when you have this setup of more than just one master node, right? So I have the log setup here. I'm going to go and stop a master, okay? So which is actually the elected master. So this is the advantage of having running it on AKS or on Kubernetes per se, where Kubernetes would make sure, this is like a disclaimer actually, where if you bring down a pod or a node or a pod actually, Kubernetes it itself makes sure that it will bring it up later because it doesn't know that I actually wantedly brought it down, right? It probably would think, okay, some network failure or some resource failure or something like that. So just to keep a disclaimer here, because even though I stop the pod here, Kubernetes would determine it and will bring it up very soon, right? So let's see, but that's not our use case here, right? We wanted to see what happens if it goes down and what happens when for the election process. So I brought the elected master down. Let's see, it will take probably some minutes, or sorry, not in minutes, a couple of seconds for it to delete it. And then let's go continuously click on it, and you can see it is actually still 0. And here I can see if it actually, okay, it's terminating with a couple of seconds. Yep, that's it. So I think, yep, it's still, but here, look at the communication that happens here, right? So master 0 is down. Of course, I can log into it, but here, let's go and check it here, right? So what happens? So here you can see that there are a lot of exceptions, of course, because it wasn't able to find what happened to master 0, right? And then what happens is automatically a election happens. Let's see which is current elected master node. If you see here, master 0 is gone, and then master 2 is actually an elected master node, right? So let's go and see in 2 if we can find it quickly. So look at here, master 2, and then yep. So it's not able to communicate to master 0. And then I'm trying to find that log actually. All right, so here, this is the one. So if you look at here you can see that the nodes actually, I mean, it will be the same log on this node as well, but just because I found it, here you can understand that the node master 0 was actually out of communication, right? And it was able to sense it, okay, that there is an actual elected master node that went down, right? So and then we can see here now, yeah, so this is another cool thing about Kubernetes, but I actually deleted it again. But here, because you can see that master 0 came back and it actually joined back to the cluster. But again, that's because Kubernetes brought it up. But if you're self-managing it, this step wouldn't happen, and you have to probably set up alerts and other things for the data for the nodes to come up. Okay, so this is just one process of looking at what happens when actually elected master goes down. So now master 2 is elected master, and then because I deleted the master 0 again, it just didn't come back yet. Now let's quickly go back to the next step of process that we have. Now, just for the communication process, like let's see what are the logs that would look like when I go to the data node. So here we can see that these are the logs, right? So now the purpose of this thing, I'll just change the transport layer to trace, and then you can see. So this is master. You can see how, like this is how you can see that how these nodes are actually communicating with each other. Of course, it's very tough to go to exact log what exactly the communication is going on, but here you can see that there are constant pings or constant communication that happens between the data nodes, right? Now I'll just put it back to info to keep the logs clean. And then let's go. Now let's see what are the communications that happen in the master nodes, right? And what are the responsibilities of the master node quickly. So now I actually created a new index, which is for the same settings and same mappings, just for the testing purpose. And let's see what goes on here. Look at here, the steps that happen. So just remember, creation and deletion of indices is the primary job or one of the main job that master node performs, not the data nodes, because the data nodes doesn't have the responsibility to create an index or delete an index, right? So here we can see that when I executed that command to create an index, which is orders new, different than the older index, it actually gave me shards acknowledge true, and then it actually created, gave me an acknowledgement, right? Here you can see what is the log message that you get. So it went to master 0, 1, and 2, right? Now, using this, you can easily understand that elected master node, which is 2, 0, 1, and 2, actually took that responsibility of creating an index. So it got created index, and then how many of the shards, so what is the cluster UID, and stuff like that. And then initially, it will be yellow because yellow, green, and red are a couple of different states. We'll talk more in the next session. It went from yellow to green automatically because it was able to set up all the 5 shards of this node, of this index across. It was able to allocate them. So that is pretty much it for the creation process. Now, when you go to delete of it, so let me take it out here. When I go to delete of it, right, delete it, and here you can see that, the index has been deleted, right? This is just a creation and deletion process. Now let's go back to, so I created index and I deleted index, all good. Now let's go back to the other one that we have, that is, okay, so this is my existing index where my app is continuously writing, right? So my app is continuously writing, and then I can actually see that the documents are actually increasing as well. Earlier, when we started, we actually had 2,000, and then now it's 3,748. So this is my, you know, uh, the shard allocation of this particular main index where the data is actually writing to, right? Let's check the next one. So we actually saw what happens when elected master went down, all good. Elasticsearch was able to elect a new one, all good. But let's see what happens when a data node goes down, right? We'll actually make a data node down. So if you can see shard 0, the primary of it is actually there in 3, but the replica R is actually there in 2, right? Let's bring down a node, in this case 3, where the primary of the shard 0 is there. And let's keep on see what Elasticsearch does, right? In the meanwhile, what we can do is to change it to debug. Let's see the communication so that we'll see much more information. And then let's see what happens between the communication here and how does promotion happens, right? So I'm going to bring down a data node. And let's see if it's still terminating. I think it's terminating. A couple of more minutes. And then let's see what happens here. So we just remember we just removed data node 3, and so look at that. Automatically, whatever the shards, I forgot to copy, but if you remember, there was actually the 0th primary was there in 3, and the replica was there in 2, right? Now what happens was, after when the 3 was brought down, the replica of it was there in 2, correct? Earlier, automatically Elasticsearch will promote that replica to a primary, so that your data isn't lost and the write operations aren't affected, right? So if I copy this, so here you can see that all the communication goes on, that what happened, data node went down, and then here also you can see that the data, that the Elasticsearch, because I brought down data node 3 for sure. So all the other nodes actually communicate with each other, right? So I just copied this for now here, just for let's hit on this. unassigned. Yeah. So if you look at this, I mean, of course, I can keep on continue that, right? So here, 3 went down, right? So 3 went down, but if you see these two, the replica of 0, earlier, which was still unassigned, it took some time, but the data isn't lost, right? The primaries are up and the data is still coming in. And the primary actually started by the time we again executed the request, and the 2 actually took the responsibility of primary of 0, and the replica, which was unassigned initially, was actually assigned to 0, right? Similarly, this was unassigned, but here, just as when we executed the request, it actually went to 1. So this happens when the nodes get down, and how the replication process happens, the promotion of replication happens, automatically is taken care by Elasticsearch. Now, just one more thing. I think Cube actually, okay. Okay, Kubernetes already brought the data node tree up. We'll just end the demo with just one more thing, right? What happens when a search query is executed? Just quickly is now I have the data, and of course, now because 3 is back, it again rebalances and everything is taken care, because when 3 comes up, Elasticsearch will realize, oh, no, there's a new node which joined the cluster, but then it has no shards. So let me rebalance, right? So it will automatically see, okay, these 4 nodes were overloaded, kind of. So let me rebalance so that all 5 will be in a balance, right? So then let's see what happens when I do a search. Now, if you look at here, right? So these are 5 data nodes, and I'm just going to see how the communication happens and just show you high level when a search query is executed. Now, look at this, right? So you may be thinking why the query was hit. And of course, the kind of logs that we have now is only for query and fetch, not like a request. So we don't know actual request went to which node, but we can actually see that the query and fetch components were actually came to these nodes, like 0 and 4, 3 and 4, right? So here you can see that each node, wherever this request has come, actually returned some hits, like 767 hits here, 775, and then you can see 795 and 753 and so on. So this is just to show you a very initial level of communication that happens between the nodes. Now, just I think we're pretty close on time. I think we can probably end it here, I would say, for the demo part, and then we can go with questions.
Cool. Thanks, Shri. So that's pretty much it. What I had, or what we had for today. And now, any questions? Anything from anyone on the call? Cool. The question is, how do you like to monitor your primary Elasticsearch cluster? Regarding logs in the console session isn't very good unless you are troubleshooting for sure. Do you have a separate logging cluster? So in our experience across our projects, we have seen different ways of monitoring and looking the logs from Elasticsearch, right? In 2014 and 15, when we started, we went ahead with our own implementation of Influx and then Grafana on top of it, right? And then we were routing all the logs from Elasticsearch containers to Influx, and then from there to Grafana. In the last couple of years, we have also started using a separate Elastic APM based cluster, and using the metric beat, we can push all the logs and some more metrics to that separate logging cluster, as you mentioned. So definitely, yeah, no one likes to read from the consoles, right? So in order to search, Elastic APM is a pretty good thing, not just for logging and other things, but then we are using it for some of the projects for even apps monitoring as well, or API monitorings as well. So yep, that's how the option is. And in some places where we are using Kubernetes-based implementation, using ECK, we have routed it through Prometheus, and then from there to Grafana. Different options, many options. You can route it to Splunk, you can route it to Datadog as well.
Yeah, one other main thing is what happens if that goes down too. Like if you have in the same cluster, you should have a separate logging cluster. Yeah,
Oh,
if it
for sure, for sure. If you have, let's say, 4 or 5 environments, you want to keep your logging things outside, right? And then probably bring all of the logs from all the environments to the same logging centralized logging system or monitoring system.
probably next session we would plan to show them about the basic monitoring that we can set up as a demo.
Yeah, we can implement that based on Prometheus and Grafana in this case, or maybe an APM cluster. We can think about that. Any other question?
Doesn't look like there's any other questions. If you're watching this not live anymore, feel free to comment on this YouTube video, and we can try to get some of these questions answered maybe next time, Praveen and Shri, and we'll be doing another meetup with these two on November 3rd. So keep an eye out for more details on that. And it looks like we have one that says, I would love to see your centralized logging setup. So maybe that's for
sure.
meetup.
Cool. We have more ideas for the next few sessions, not just the next, but the next afterward as well. Pretty good. Cool. As Olivia said, we will have one more session where we will talk about administration or operational features, or not features, actually, the work that you have to do for Elasticsearch if you are operating an Elasticsearch cluster. So that's on November 3. It's Wednesday, 1 p.m. Central, and you would hear from all three again.
Thank you, guys.
Thanks, everyone. Bye-bye.